appreciate it. And we'll move on to our last talk for this session. Let me get things set here. So our last talk is by Jessica Werk from the University of Washington. And she's going to tell us about discovery of a sample of quasars behind the galactic plane.
All right. Hi, everybody. It has been great to learn so much about quasars and what intrinsically fascinating sources they are. In this talk, you're not going to learn anything about quasars themselves, other than the fact that they are incredibly useful as probes of very diffuse material in front of them. And that is why ultimately I'm interested in quasars. And I'm going to tell you a story about how we have discovered a very unique sample of UV bright quasars behind the galactic plane of the Milky Way, and why these very rare quasars are absolutely crucial for testing models of how gas is distributed in the Milky Way. And so the first half of this talk is just explaining to you why this is interesting at all. And this is one of my favorite images. It's one that my colleagues and I included in our annual review article, the first annual review article of the circumgalactic medium. It is meant to illustrate that the circumgalactic medium, or CGM, is really the key mediator of the galactic gas supply. It's where outflows meet inflows, and it turns out to be a dominant reservoir of gas in our own galaxy and in other galaxies throughout the universe. And so it plays a very important role in galaxy evolution and the so-called cosmic baryon cycle. And the installation of the cosmic origin spectrograph on the Hubble Space Telescope was really a game changer for CGM science. And it was installed right as I became a postdoc, and I dove in to circumgalactic medium research with the survey that was called COS Halos, which was one of the first surveys to prove that, you know, all galaxies like the Milky Way, all massive galaxies, are surrounded by these enormous reservoirs of ionized diffuse gas known as the circumgalactic medium, extending out to hundreds of kiloparsecs beyond the galaxy's stellar disk that is just so beautiful and sparkling there on the sky. And so here's a fun fact about the CGM for you. The majority of the atoms in the air that you are breathing right now, the air that you've been breathing your whole lives, in fact, actually spent several billion years out in the circumgalactic medium, far from the Milky Way's disk. So more than 80% of them did. So in this way, studies of the circumgalactic medium have the potential to really reveal our cosmic origins. And so here's 3 fun facts about the CGM that'll get you up to speed on what we know about the circumgalactic medium. And all of these images come from this annual review article, 2017, Tumlinson, Peebles, and Werk. Check it out if you're interested. But generally speaking, the circumgalactic medium is traced through a wide range of different ionization states of both metal lines and, of course, neutral hydrogen. And so because it's traced by a range of these ions of varying ionization potential energies out to, like I said, hundreds of kiloparsecs, and on the x-axis there is an impact parameter between the central host galaxy and some background quasar line of sight in the rest frame of the galaxy, right? We're using quasars as background probes now for gas in front of them. We call it a multi-phase medium. It's gas of different densities, of different temperatures, and this is a fake phase plot, but you can see this range of different ions that you can see in absorption at various redshifts in the foreground of the quasar that are tracing circumgalactic material. The one that I'm going to talk about is carbon-4, which is a doublet at 1548 and 1550 angstroms. And so we trace the circumgalactic medium through this range of ionization states. It's a multi-phase medium, much like the interstellar medium of the Milky Way. And finally, most of this gas in the circumgalactic medium, when you look at its velocity, how it's moving relative to the host galaxy, right, which we know its velocity well because we have a spectrum of it, it's not moving very fast, plus or minus 150 kilometers per second. So I was just listening to these amazing, mind-blowing talks about gas moving 28,000 kilometers per second or something. Most of the CGM gas around normal galaxies is basically well confined to the halo itself, moving, within plus or minus, like I said, 150 kilometers per second, often much, much more slowly than that. All right, so the question that I have been obsessed with over the last, few years, I would say, is how does the Milky Way fit into this picture? This turns out to be one of the hardest questions to ask for a bunch of reasons. The key one being that we're actually orbiting a star that's within the plane, within the disk of the Milky Way, surrounded by a gigantic high-density interstellar medium that absorbs at the same velocities that the circumgalactic medium would be detected at. And so we've got this huge foreground problem because we're like a meatball in a plate of spaghetti trying to figure out, how much spaghetti there is, but all you see is the spaghetti right in front of your face. And so, so you can kind of see this here. We have to account for blended absorption from the foreground ISM if we have a chance of understanding how much material is in the circumgalactic medium of the Milky Way. Now, historically, people have done this work. Of course, there's a rich history of studying what are called high velocity clouds that are in the halo of the Milky Way, part of this galactic fountain. But like I said, most of the circumgalactic medium in other galaxies, at least, is moving at much slower velocities, right? Closer to a systemic velocity of v = 0. So how do we find that low velocity halo gas, which is expected to be the bulk of the gas in the halo? And so in 2017, there was this discovery that high ionization state lines like carbon-4, if you look at quasar lines of sight that in the Milky Way halo that are separated by 2 degrees, 3 degrees or fewer, these high ionization state lines like carbon-4, right, that are tracing gas at around 10 to the 5 Kelvin, very low densities again, but there's not a lot of change, right? Like it's uniform on large angular and spatial scales, this carbon-4 absorption. So we designed this experiment that I thought, oh, for sure, now we're going to learn about the Milky Way. And the experiment is to isolate the low velocity gas in the circumgalactic medium using very close sightline pairs of stars and quasars, right? So the star is at about 10 kiloparsecs into the halo, and the quasar is at a distance of infinity, right? It's tracing the entire halo of the Milky Way. So if you subtract the stellar absorption, which is just basically the ISM, from the quasar absorption in carbon-4, you're left with a deblended low velocity measurement of the carbon-4 in the Milky Way. And so we have this program. We thought this was a great idea. We actually sold it to the Hubble Telescope Allocation Committee. We called our survey Quastar, right? Because these are quasar star pairs, all separated by less than 2.8 degrees on the sky. The quasars we actually drew from archival data from all the quasars that have been observed with COSS. There are hundreds of them, and we found halo stars that were closely matched, UV bright halo stars, where we knew their distances, and then we were going to use this subtraction technique. And like I said, it's just a very simple thing. You've got the stellar spectrum in red and the quasar spectrum in blue. You expect to see maybe a little bit of excess. You do this alignment and you subtract and you get a little bit of excess, and maybe you can see how much carbon-4 there is in the CGM of the Milky Way. Some lines of sight might trace structures that are moving at high velocity that are in the halo technically, like the Magellan Extreme, but that's kind of a weird structure. But our main question that we wanted to answer in our study of the carbon-4 content of the Milky Way's halo is this warm circumgalactic medium in the Milky Way different from other star-forming galaxies of similar masses? And so you can see this plot here. This is what's called a covering fraction. It's basically a detection fraction of carbon-4 around other galaxies as a function of this, what's known as the impact parameter. And you can see that it's very high covering fractions within, half a virial radius between 50 and 80%. Well, what did we find in quasar with our 30 quasar star pairs? Oh my gosh, about 20% covering fraction of low velocity gas. And we were like, okay, so maybe the Milky Way's warm CGM is different from star forming galaxies. Maybe. I wrote yes there, but the answer is still maybe. Why don't we detect more low velocity carbon-4 in the Milky Way? There's a ton of reasons that we could come up with. However, the one that I am now convinced might be the case is that we're totally missing the majority of the circumgalactic medium content, because the CGM is actually arranged in a giant disk-like structure, okay? And now this isn't totally insane. There are simulations, there are observations at low redshifts of, along extragalactic lines of sight at different orientations along the major axis that indicate at least some of this ionized material might actually be arranged in a kind of disk-like morphology extending out to 100 kiloparsecs, which, okay, it seems a little crazy. But the thing is, every line of sight that probes the Milky Way halo is basically at a galactic latitude above 30 degrees, avoiding the plane. It's really hard to find low galactic latitude quasars, but if we had them, we could test this hypothesis. And so that's where this entire experiment came from. We generated some toy models. We figured out that only at galactic latitudes less than 30 degrees would you be able to detect an absorption signature in some ionized component of this kind of flared ionized outer disk model. And like I said, another challenge, aside from being in the disk of the Milky Way, is that every single line of sight in the archives, and the quasar lines of sight are in pink here, are at mostly galactic latitudes above 30. That's that second line. We've got the line through the midplane, all the stars that have been observed with COSS. And then most of those quasar sight lines are above 30. 95% of them are above 30 degrees. Okay, so the solution was we selected photometrically a sample from GalaxCOSS, which was like an end-of-life Galax survey for UV bright objects in the plane of the galaxy. We teamed up with David Shimonovich at Columbia University. We did a lot of cross-matching of catalogs, blah, 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 selected some what we thought were pretty good candidates of quasars. But of course, this is only photometric selection. And so what we did is we went after these 305 UV bright quasar candidates in the galactic plane with the APO 3.5 meter and the MDM 2.4 meter. We ended up confirming a sample of 64 low galactic latitude UV bright quasars, most of them with the APO 3.5 meter. And so what would this talk be? I know I'm running out of time. Or maybe I've run out of time. Oh my God, I'm so sorry. I just wanted to show you a few spectra that we took with APO, just because this is a talk at an APO science conference. You can see here a beautiful quasar at redshift 0.648, another beautiful quasar at redshift 3.19. This is a really cool tool called MARS, by the way, M-A-R-Z. It's just a fun web browser. You can put any fit spectrum in and it'll just give you a template. It's really fun. But you can see we've confirmed. Now, sometimes we find stars. That's our main contaminant. Here is the distribution of the newly discovered low galactic latitude quasars. And most excitingly, right, because we were able to confirm this sample of low galactic latitude quasars and convince the Hubble's Telescope Allocation Committee again that this was an experiment worth doing, that we had to discover the Milky Way CGM, we were just awarded 71 orbits with the Hubble Space Telescope Cosmic Origin Spectrograph to look at these low latitude quasars and look at them in carbon-4 to see if there is going to be any detection of this giant ionized disk in the Milky Way. So solving this CGM anomaly might be on the horizon thanks to the APO 3.5 meter telescope. Thanks everyone for your attention.
Thank you, Jessica. Let me just say, that's really exciting and interesting stuff. All right, so we have questions from Don first.
Yeah, you still have some limit of column density of hydrogen or dust or something that you can't see these quasars. Can you give me a rough idea of AV or hydrogen column density beyond which you don't find any?
Yeah, exactly. I mean, the key is to finding the UV bright quasars. We're kind of looking through these like serendipitous holes, basically. The EB minus V, this, SFD, Schlegel, Finkbeiner, David, ranges from 0.05 to like 0.19 in some of these cases. So we did a lot of modeling when we sold the cost program to make sure that, the extinction isn't just going to totally kill us. The obscuration isn't going to totally kill us. And when you're looking through the disk as well, in hydrogen, you're totally screwed, right? Like we cannot look at these in Lyman alpha as a result of the fact that it's just going to be fully saturated. We're going to be in the wings. But this high velocity component, let me scroll back here. Oh my gosh. You can see this high velocity component. We've modeled it here. We've done this kinematic model, and we're expecting column densities of carbon-4 at velocities separate enough from this kind of like disk carbon-4, which doesn't saturate, of like 10 to the 13.5 or so, if it's similar to other galaxies, atoms per centimeter squared.
Okay, I think we can take one more question, Bryson.
Yeah, thanks. I was just wondering why you went with carbon-4, or were you trying to search for this more ionized gas? And do you have any plans to also go back and look for other phases of gas with like magnesium-2 or oxygen-6 or something like that?
That is just a great question. So carbon-4 is one of actually the highest ionization potential line that's available with COS at redshift 0. And the reason we wanted the highest ionization potential energy transition is just that it turns out the CGM is very highly ionized, and most of its mass is in these high ionization state, low density kind of tenuous material. However, magnesium-2 is a great idea. It would be fun to do that. I don't know what instrument I'd do that on. 2798 angstroms at redshift 0. That's like near UV kind of observations. And then, of course, with our COS data, we will see silicon-2, silicon-3. The problem is the Milky Way disk at those low ionization state lines is super saturated. And so it's much harder to make out other components. The Milky Way disk in carbon-4 is not saturated. And so that's one of the main reasons, like that's one of the few transitions in which we think we can see it, or we should be able to see it.
Thanks.
Awesome.
Yeah.
So any remaining questions, please put on the Slack channel. And thanks once again to Jessica and to all of the speakers in the Quasar session. So great job. Nancy, do you have anything to say before we take a break?
Nope.